Hi, everyone. Excited to be here. My name is Sunnie. I'm a PhD student at Princeton. And today I'm going to tell you about our work called HIVE, Evaluating the Human Interpretability of Visual Explanations. And this is a work done with Nicole Meister, Vikram Ramaswamy, Ruth Fong, and Olga Russakovsky. Also, all of us are here, so yeah, please come say hi. So as we all know, the interpretability research field has seen rapid growth in recent years, but evaluating interpretability methods remains a challenge, particularly due to the diverse ranges of proposed explanation types. There are heat map explanations that attempts to explain why the model has predicted a certain class, but there are also more complex explanations like these on the right, produced by these more recent interpretable by design models that reasons with prototypes. And while not on this slide, there are a number of other approaches ranging from example-based explanations, concept-based explanations, contrastive and counterfactual explanations, and so on. So we argue, as more diverse interpretability methods are being proposed, it's more important than ever to have a standardized framework for interpretability evaluation. To this end, we present HIVE, which is a human evaluation framework for visual interpretability methods. And we really try to design this framework with three principles.
Sunnie, sorry to interrupt. The slides are not changing.
Oh, they're not showing on Zoom?
They are showing, but we're still on the title slide. I don't know if that was intentional.
Oh, okay.
How did this happen? So I'll have to resume share.
No, we can see the slides. It's just they're not changing. They're on the title.
Yeah, so
okay, now I can see our contributions slide.
Because when I do the full screen, it actually pauses the sharing for some reason. Because okay, so I know.
It's good. Oh, now we can't see the slides.
Yeah, I'm gonna actually share the whole desktop.
Okay, got it.
Now. Okay, can you see the slides changing?
Yep. All good.
Okay.
All right.
Do you want to restart or continue?
No, I think I can just show this slide. I guess the point was to share that there are many different forms of explanations, and these are the four methods that we evaluate in our work. So we wanted to show like visual examples for them. So yeah, going back to this slide, we designed this framework with three principles in mind. So first of all, we wanted to move away from intuition-based justifications and towards evaluation that would enable us to do falsifiable hypothesis testing. And second, we wanted to complement existing algorithmic and often automatic evaluation metrics with a more human-centered evaluation. And finally, we wanted to go beyond evaluation methods that only apply to one type of method. So a lot of like automatic evaluation metrics only apply to feature attribution heat maps, which are great, but we wanted to develop a framework that would enable us to compare different types of methods, such as the heat maps, but also prototype-based explanations and other forms. So to state our contributions up front, we present and analyze a new human study design and use it to evaluate for existing interpretability methods. So we actually conduct human studies to evaluate existing work. Next, we investigate an understudied property of explanations, so the utility of explanations in distinguishing correct and incorrect model predictions. We also conduct the first human studies for interpretable by design models, and also study like user preference and behavior, such as how users trade off interpretability and accuracy under different settings. And finally, we do open source our framework so that more future studies can be done with them. And we also wanted to encourage more human-centered approaches to interpretability research, because at the end of the day, interpretability is a human-centric property. So here's an overview of our HIVE study design. At the core are these objective evaluation tasks that would enable us to test certain falsifiable hypotheses. And because we wanted to do a human-centered evaluation, we really focus on testing the utility of explanations to human users in AI-assisted decision-making scenarios. In particular, we focus on whether explanations can help us distinguish between correct and incorrect predictions and design two tasks for this purpose. So we first have an agreement task where we show an image, a model's prediction, and then an explanation for the prediction, and ask the users whether they think the model prediction is correct based on the explanations. And this allows us to measure how much confidence explanations instill in the model's prediction. And secondly, our main evaluation task is the distinction task, where now we have one image, multiple prediction options, and then explanations for each. And now we're asking users to pick the correct class based on the explanations. And here we're trying to evaluate whether the explanations for correct and incorrect predictions are different. Also note that we don't show class labels intentionally because we want the users to focus on the explanations rather than use their prior knowledge in completing this task. So we show them as like class A, B, C, D, or class 1, 2, 3, and so on. HIVE also allows for cross-method comparison because we evaluate all interpretability methods on a common task. However, because these different methods are sometimes developed with different purposes, with models trained on different data sets and such, we do create individual evaluation UIs that respects the method's characteristics, such as its explanation form or the data set used for model training. So here I'm showing example UIs for evaluating ProtoPNet on the agreement task and GradCam on the distinction task. And we also note that for some of the more complex explanations, we do make adaptations so that the evaluation task is doable for participants who might not have too much background in machine learning. Okay, so here's a brief overview of our experimental setup. Using HIVE, we evaluate 4 existing methods. These are GradCam, BACnet, ProtoPNet, and ProtoTree. And these cover the range of postdoc explanation methods to the more recent interpretable by design models. And yeah, for each study, we recruited 50 participants through Amazon Mechanical Turk, and finally evaluate the property that we're trying to measure with the participants' task accuracy. So we gained a number of interesting insights. In this talk, I'm just going to go over 3. So our first key finding was that participants tend to believe that a model prediction is correct when given an explanation for it. So here I'm showing you the agreement task results separated by data set and also by whether the shown samples were indeed correct model predictions or incorrect model predictions. And what we see here is, so for each evaluated interpretability method, I'm showing the percentage of predictions that the users thought were correct. So what we want to see is we want all these green circles to be close to 100, and then we want all of these orange triangles to be close to 0. But what we actually see is that they're all over 50, which would be the random chance when people randomly pick choices. And what this suggests is that when given an explanation for a prediction, more often than not, participants would think that the model prediction is correct, revealing an issue of confirmation bias in interpretability work, and also raising some caution against explanations potentially engendering overtrust in AI models. Our next key finding is that participants struggle to identify the correct class based on the explanations. So here I'm showing you our distinction task results, again separated by data set. But here on the y-axis now, I'm showing the mean task accuracy. So when participants were given 4 prediction options, they are asked to make a choice for 1. So our random chance baseline would be 25%. And here we would want, because this is task accuracy, we would want all of these numbers to be close to 100. But they're not, which is our first observation, suggesting that interpretability methods should be improved so that they can better identify and explain model errors. But another interesting thing you can see here is that the accuracies are indeed higher for correct model predictions than incorrect model predictions, suggesting that explanations for correct predictions might be more coherent or convincing or distinct than those for incorrect predictions. Lastly, we study interpretability accuracy trade-off by asking participants to input the minimum accuracy of the baseline model that doesn't come with any explanations that would convince them to use it over the model with explanations. And here, on average, we find that participants require this baseline model to have 6.2% higher accuracy in low-risk settings, 8.2% higher for medium risk settings, and then 10.9% higher for higher risk settings. And these below are some examples of different risk settings that we presented to the participants. So with that, I'm going to conclude with this slide that just gives an overview of our contributions again. And here are my co-authors. Yeah, if you want to learn more about our work, we put a project page link, and I'll also be at the poster session. So yeah, I'll see you there. Thank you.
Sunnie, we have one question on Zoom for you. The question reads, I'm curious about how to use the methods such as GradCam to do jobs such as prediction as class A because of so-and-so reason. Were you able to hear me?
Yes, I was able to hear you. I'm trying to understand the question, which seems to be asking, so grad cams are like post-hoc prediction, like explanation methods that, sorry, is the person who put the question like on here? Can they maybe clarify the question? It seems like they're asking like, how can we make, causal claims or, make any statements about causal relationships when these explanations really talk about like correlations of how a prediction was made, and yeah, but I wasn't sure like what the question is exactly asking.
Let me see if this person is.
I guess in the meanwhile, I can say, I guess we're not trying to evaluate like whether these explanations are indeed explaining causal relationships, but we do want to evaluate, we do believe it's like an important property for explanations to have, to be able to distinguish between correct and incorrect predictions. So I think, yeah, that was the property that we were trying to test with this framework.
Okay, actually, I also have one question. First of all, it's great to see work on benchmarking explainability in computer vision. I feel like we have been missing that kind of work. I have one question when you were splitting explanation based on the explanation type and similar things like that. Have you ever considered actually also splitting based on who are the explanations meant to? So it can be a layperson or a model designer or a regulator.
Great question. In this framework, no. I think the implicit assumption behind all of these methods are that they're mostly meant for like computer vision researchers or model designers who have some background knowledge. I guess we really try to make them more accessible to, I guess, people with limited ML background. But because we weren't sure what each of the methods, like what was behind like the method designers, like what their thoughts were, like whether they meant it for like really XAI researchers or computer vision researchers, or like users who might not have ML background. I don't think we try to do that categorization in this work.
Okay.
But I do think it's like a very important property and something we should keep in mind.
Thank you. Okay, second speaker, if I managed to get, okay. So, Yu Yang. Okay, maybe try to speak closer to the mic. If people have issues hearing, let us know.
Okay, hi everyone. I first want to thank all the organizers for bringing us here together today. And my name is Yu Yang. I'm a PhD student at University of California, Los Angeles. I'm very happy here to share our work in this spotlight session on explaining deep convolutional neural networks via latent visual semantic filter attention. Deep neural networks have become the go-to solution when people want to learn from a large amount of data to make predictions. It seems now that deep neural networks is all we need, or is it? Predecessor models like linear regression, I'm showing on the left, make predictions based on explicitly predefined features. Therefore, these models are interpretable by definition. On the contrary, deep neural networks learn features implicitly. As a result, we call these models as black box models because we cannot understand the cause of their decisions. Are they using fair and reliable features to make these decisions? We don't know, but we have to find out to make sure they are not impacting our society negatively. So a deep neural network is not all we need. we also need to know what it has learned from the data. In this paper, we study one type of deep neural network, deep convolutional neural network, or deep CNN for short. We consider each convolutional filter as a neuron. Given a trained deep CNN, if we know the features learned by each convolutional filter, we can turn this initially black box model into an interpretable one. So existing XAI tools for image classification models usually focus on different settings to provide complementary information from previous work. We first want to clarify the difference between their settings and what we want to do. So as introduced in the previous presentation, so we have this saliency method. They visually show the amount of contribution for each pixel to the model's prediction. However, they aim to explain single predictions, now not the model, and they explain pixel level features, not the high level semantics. And they also require users to speculate meanings of the visualizations as they do not provide explicit semantic explanations, like saying this is a dog, etc. And on the other hand, interpretable CNNs, they're more meaningful representations with special losses or network designs. And then by design, they cannot interpret representations learned by any given network without changing its structure or retraining. Another work that is closest to ours is network dissection. It interprets latent representations, but it cannot explain concepts that are not in the predefined set that is used to train the explainer. So the main objective of this paper is to propose a new XAI tool for deep vision models that can overcome the limitations of the previous work. First, we expect it to provide explanations that are more semantically meaningful and objective than visualization-based methods. Second, we wanted to explain any trained network, any given network, without knowing the original training data or any information about the training process or retraining. Third, we hope it can generate explanations using novel concepts that are not given in the training set. We set this objective based on realistic setting in practice when one needs to interpret and scrutinize a given trained model. So we proposed LaVice, a latent visual semantic explainer for deep convolutional neural networks. For each convolutional filter of a trained deep CNN, LaVice can provide both visualizations and semantic explanations for the feature learned by this filter. We designed two key components for LaVice. The first key component is this latent visual semantic mapping. We learn a mapping function whose source domain is the latent visual feature representation space, and a target domain is a well-learned semantic space. This mapping function is trained contrastively so that each visual representation is mapped closer to the related semantics and farther from unrelated semantics. So I had like animations here, but since we are using PDF, I cannot show the animations to you. So with this mapping function and the learned semantic space, LaVice is able to find the more accurate explanations for any given filter, even if the concept is not labeled for the image dataset. And the second key component is filter level attention. It allows us to more accurately explain features that are distributed over multiple filters. When Levi's is explaining one of the filters, and we call this filter the target filter, it assigns weights to all the other filters based on how similar their activations are to the target filter's activation. And then the weighted combination of all filters is used to explain the target filter. Well, existing work either cannot provide explicit semantic explanations or is restricted to explaining with only labels in the training data. Levi's can provide both visualization and semantic explanations with both annotated and zero-shot concepts. Plus, Levi's can provide more accurate explanations with the proposed filter attention. We show with our extensive experiments that Levi's can find zero-shot concepts to give more accurate and comprehensive explanations than using only the annotated labels. Here, words in red are concepts that are not used for training Levi's. However, Levi's can still discover these more accurate words with the two proposed key components, latent visual semantic mapping and filter attention. Levi's can not only unveil features learned by a network, but also help provide insights of unlabeled data sets with a pre-trained model. By looking at the highly activated filters of each image and the corresponding semantic explanations given by Levi's, we can get a big picture of the data set and even find potential biases in the data set if we have gender or other demographic labels. To conclude, in this paper, we propose a normal framework that can both visually and semantically explain latent representations of a trained CNN. It constructs the mapping between the visual and semantic spaces with a contrastive loss and explains distributed features with filter attention. With the recent development in multimodal and contrastive learning, the feature mapping part of our method can be further empowered by incorporating the state-of-the-art algorithms and techniques. Please check out our paper to see more details and results, and also you're welcome to discuss with us in the poster session. Thank you so much. Do we want to answer one by one?
Dipti, do you want to go through the questions or?
No questions on Zoom at the moment.
So the questions that we see in the chat for the previous presentation?
Yes.
Okay. You can use a microphone, yes. I think will have to repeat the question.
Yeah, I was wondering to what extent you think, because you're mapping the two representation spaces together, to what extent do you think you might be learning the biases in the language model space? Because, you know, the language model might assign doctor or nurse different probabilities to different genders. Do you think that's an issue, and did you think about that at all?
Yeah, I think that's a good question.
Can you maybe repeat the question? Because on the Zoom, they cannot hear.
Okay. So the question was that since we are using some trained semantic space, and we may have some biases in, for example, trained word embeddings, etc. So do we think that is going to affect the explanation, or kind of also have the biases in our explanations, right?
Yeah.
Yes, I think that's a great question. As you can see in our results, so our method can also use to discover the biases in the image data set. So I think it could be that we have biases in the trained semantic spaces, and therefore we also like have these biases, but in this work, we are not trying to mitigate these biases. And yeah, it will be interesting to see if we can further maybe use our work or adapt our work to discover these biases also in the semantic space. Yes, thank you.
Thank you.
Thank you so much.
There is one question for you on Zoom. Can Levi's work for networks with higher level tasks such as object detection, pose estimation, etc.?
Okay, thank you. So for this work, in our experiment, we only tested image classification, but I think it can also be transferred to other tasks such as object detection and pose estimations, as mentioned in the chat, because we are only looking at the feature extractor. So like the downstream task, it doesn't matter that much.
Thank you.
Thank you so much.
Okay, the next talk is Subash. In the meantime, I'm also gonna try and kill my email notifications. They don't go off when I need them, but now they are. Okay, so we start this.
Thank you. Hello, everyone. My name is Subash. I'm here to talk about our work, Causality for Inherently Explainable Transformer, which we call CAT-XPLAIN. So neural networks have proven to be excellent function approximators, mapping input space to the output space, solving diverse range of problems for us. Now, we as a community, we have developed very accurate models which are right most of the time. It's high time that we make sure that we are right for the right regions, especially for the critical applications like medicine. Therefore, there have been different post-hoc techniques and post-hoc explainers developed. The goal of explaining pre-trained black box neural networks decisions. One of the approaches towards developing post-hoc explainer is through causality. In this family of explainers, it is assumed that there is a causal relationship between the input space and the output space. Therefore, by simulating the breakage of this causality, we can identify the most important input features that were contributing to the black box model's decision. And this has been demonstrated by an earlier workshop paper by Pranoy and his team, where basically what they do is, given a pre-trained black box model, they propose to train an external explainer, E, such that it produces a categorical distribution from which a fixed set of features, in our case, features would be the input patches if it's input image, fixed set of features can be sampled from. As we can see on the right, this explainer is trained with the selection loss. And we also can see that both of the components of the selection loss, P of y given x and P of y given x of s bar, those both are obtained from the pre-trained black box model, while s bar being the set of input patches with the least causal importance. So once we train this explainer, we can identify the input patches with the highest causal importance. While the post-hoc explainers like this are a good way to understand the behaviors of the pre-trained black box model, we can notice that this is trained in isolation with the black box by being just guided by the output of the black box. So it's entirely possible by that these post-hoc explainers might be learning different feature representation and maybe focusing in the different regions of input. Therefore, there is a need for inherently explainable models. In this line of thinking, we propose inherently explainable vision transformer. This can be called explainable VIT, XVIT here. This is a standard vision transformer that takes input image as a sequence of patches, passes through a linear projection layer, and then adds positional embedding, and then passes through multi-headed self-attention series to produce embedding for the classification through classification head. The only modification we proposed here is to bring in the previously discussed instance-wise causal feature selection approach into the training of the vision transformer itself by adding just one extra learnable token. In this case, it's a token denoted by SEL in this figure, so that the selection head can consume the embedding and then produce the categorical distribution from which the top features can be, top patches in our case, can be sampled. We train our explainable VIT through this combination of loss. This is the standard cross entropy plus the selection loss that we discussed earlier, lambda being the hyperparameter, simultaneously. So once trained, our explainable VIT is able to make the prediction through the classification head, whereas also identify the most important, causally important patches through the selection head. We evaluate our model with two of the explainability metrics. These are post-hoc accuracy and average causal effect. So post-hoc accuracy, this computes how often does the prediction of the model matches when the model is given the full input X in this case, versus the model is given only the selected patches as input. When I say only the selected patches, only those selected patches were left while zeroing out the rest of the patches to simulate the breakage of the causality. So that's what the post-hoc accuracy computes. So higher the better. And average causal effect is the difference in probability for the true label when the model is passed only the selected patches, selected by the model, of course, versus randomly selected patches. That difference is average causal effect. And we follow the experimentation of the paper that I talked earlier, and experiment on a subset of 3 data sets and compare between the post-hoc explainer's performance versus the performance of our explainable VIT. When I say post-hoc explanation, we use an identical vision transformer for both black box model and the selector model. The only difference being in the final layer MLP, of course, because for the black box, since it's a binary classification, we would have only 2 neurons. For the selector, we would have the neurons equal to the number of patches in the input. Anyway, so the fraction indicates how many, what percentage, 5%, 10%, 25%, how many the selected patches were passed. On the bottom of each of the table, we have the black box model's performance. And if you see on the right column of the explainable VIT section, that accuracy is the accuracy when the model was passed the full input as opposed to just only the selected patches. On the bottom right, we can see the demonstration of the model. For example, for the image with digit 8, the model was able to identify the patches in the left side of the image because this was trained for the classification between 3 and 8. So our inherently explainable model mostly performs better than the post-hoc explainer on 2 of those explainability metrics. However, as we can see, there is a trade-off between the explainability and the true accuracy of the model when it is past the full input. The results are reproducible in the code here in the GitHub repo here. Thank you.
I have a question for the speaker. Did you try to compare the information that you're getting from attention heads with the information that you're getting from the new selection head that you added, the new selection class token?
Thank you. That's a good question. However, we didn't compare the simple goal was to compare how the bigger picture of this is, of course, as I said earlier, if we train a postdoc explainer, then they might be learning entire different feature representations. So if we train the model both for simultaneously, both for classification and explanation, we should get better results compared to postdoc. But there are other, of course, there are different postdoc techniques that this output could be compared to, but at this moment we haven't done that.
No further questions from Zoom at this point.
So there, we can see one question on the
That's
in the
similar.
comments.
Yeah, that's what I asked. That's the same thing.
Oh yeah, we were going from a causality perspective of, so we can claim that there is a causal relationship between these patches and the output space. So we didn't explore other methods, including self-attention maps and breadcrumbs and others.
Okay, thank you. Okay, and the last presentation for this spotlight session. Just do the full screen. Here you go.
So good morning, everyone. My name is Lan Wang, and we present do not representations respect causal relationships. This is a joint work between me and Dr. Vishnu Boddeti from Michigan State University. So we know that causal models can capture the relations between random variables, which can be represented as graphs. So here, if we consider these two random variables, rain and wet flow, we all know that if rain happens, the floor would become wet. So on the contrary, if we do an intervention on the floor, for example, if we keep drying the floor in a raining day, what would happen to the rain? Actually, nothing. The rain will still keep falling. So in this case, we say the rain is the cause and the wet floor is an effect. So here comes the simple question. How can we infer causal relations? So a simple way doing that is conduct interventional experiments. For example, if we want to infer some effect of treatment on headache, we can group the patients into two groups. For one group, we let them take pills. For the other group, we let them do not take any pills. So if the group with the pills getting better and the group without pills is still having headache, we see that there is a causal effect. However, if the group without a pill is also getting better, we see that there's no causal effect in the case. However, in most applications, the data is already being collected, so it's difficult and even impossible to conduct such intervention experiments. So the only thing we can do is to rely on the observational data we already collect. So there are two main methods for causal inference from observational data. The first method is learning-based method. The key idea of this kind of method is to exploit the causal footprint, which presents in the observational data. The simple idea is that in the causal directions, like the relationships are simpler than the anti-causal directions. A second way is supervised methods. The key idea of this method is to exploit all and any possible causal singulars in the observational data through learning. So for unsupervised methods, they are agnostic to the data domain, and but it's difficult to decide no causal relation case because sometimes we need to carefully select a threshold to decide. However, for supervised methods, we can infer no causal relation case, but actually we also need ground truth causal labels to train the causal classifier. So in this paper, we focus on the question, do not representations respect causal relationships? Actually, giving some face images, actually there are lots of attributes which might be causal related to each other. So for example, here we have gender and facial hair. There might be some causal relations from gender to facial hair, And these different facial attributes could construct the face images. We know that nowadays the facial analysis algorithms could not try to predict facial attribute through learning a compact and attribute-specific representations. So in these settings, we come up with two questions. The first question is that, can we infer the causal relations in the high-dimension representations? And the second question is that, does this causal relationships in the representation also respect the causal relationships from the original attributes? We propose NCNet to address this problem. So in our model, we consider the 6 causal scenarios for pairs of high-dimension representations with and without a confounder settings. So here is a framework about NCNet. So first, we have synthetic causal feature generate model, which could generate high-dimensional representations for our training data. And next, an unsupervised branch is applied to exploit the causal footprint. And next, an adversary representation learning model is applied on the non representations to improve our generalization abilities. All components of these models are trained end-to-end to predict the final causal relations. For the details of this method, welcome to our posters for more discussion. Next part is our experimental designs. So we know that in real-world scenarios, actually, we do not have ground truth causal relations. So our solution is that we can generate controlled data with known causal relations. So there are 2 steps to generate such data. The first is to generate labels with known causal relation. So what we do is that we first generate the Bayesian graphs for all the 6 causal graphs with a hand-designed conditional probability tables. And next, we sample labels using Gibbs samplings to generate ground truth labels with known causal relations. The next step is that we sample images that conform the ground truth causal relations. So giving, like, for example, 2 factors, we sample images that conform the generated ground truth labels, and to improve the diversity of the generated images, we also add some random noise to the images. A second dataset we use is a more complex one, is Cassia web face. So for this dataset, it does not have ground truth annotations for the facial attributes. So we actually annotate 8 different facial attributes by ourselves for the causal inference. So to evaluate the consistency between the causal relationships from the non-representations and the causal relationships from the attribute labels, we propose a new metric, which is called causal consistency. So this metric is that given the set of pairs of high-dimension representations, we split into multiple long-overlapping subsets, and we measure how many subsets are consistent with the causal relation between labels. So here is our results. The first one is the causal consistency over different baselines across different causal graphs on 3D shape dataset. We can see that our NCNet has the highest and the most stable causal consistency over all causal graphs. And these results are also indicating that the non-representations can indeed mean making the causal relations in the training and representation learning process. So here, a simple conclusion is that in the control scenarios, learned attribute-specific representations indeed satisfy the same causal relations as the attributes. And here's the results for a more complex setting, the Cassia web face dataset. So in the more complex scenarios, the causal consistency decreases. However, our NCNet still has the most stable and the highest estimation of causal relationships. We also have different analyses on various settings of representation learning. So welcome to our posters for more details and discussion. So in conclusion, we have that learned attribute-specific representation indeed satisfy the same causal relations between the corresponding attribute labels under controlled scenarios. And causal relations could also positive correlative with the predictive ability of representations. More investigation is needed for complex scenarios and data with weak causal relations. So welcome to our project website for more details, and also welcome to our hosters for more discussion. Thank you.
Any questions? Okay, so I have one small question. You said that the paper also proposes a metric to evaluate the causal consistency, right? I mean, I don't know, but what is the status of, in general, metrics for evaluating causalities, especially in computer vision? Is this something that we are lacking, or?
Yeah, actually, like the goal of this paper is to want to like investigate if the causal relation in the learned representations consistent with the causal relationships from the attribute labels. So this matrix is actually to evaluate the consistency between these two. So I think in computer visions for now, most methods also try to see like if like there are also causal relationship present in presentations or some other kind of like prediction scores and associate with different objects or representations.
Okay, thank you. Okay, let me switch to my prepared slides. So this concludes the spotlight session 1. I'm really happy that all 4 speakers were in person, and thanks again for sharing your work with us. Now we are actually going to move to a poster session 1, which will also include a coffee break. So we will meet back here in roughly half an hour at 10:30 a.m. obviously local time for the people on Zoom.